All right, today we're going to talk about integration with natural log of x. So we're in section 2 of chapter 5. And just to recall from what we learned previously, if we're taking the derivative of the natural log of some absolute value x, and remember the absolute value is just there because that's the domain of logs and natural logs. The derivative of a natural log is 1 over x. And if you have something more complicated than x in there, so we'll just say u, but if that's like x squared or anything else, then it's still 1 over u, but then you have to chain rule, so times u prime. So with integrals, if we're simply taking the integral of 1 over x with respect to x, then that's going to come out to be natural log of absolute value x plus c. And you should put the absolute value in there because, again, the domain of a natural log, we can only natural log values that are greater than 0. So you can't have zeros, you can't have negatives. And then if it's 1 over u du, then you're going to get natural log of u plus c. But this one would have required some u sub. So you might have to do some adjustment before you can get it to be in the form 1 over u du. And why is this true? If you think about our power rule, normally we would say like, oh, just rewrite 1 over x dx as the integral of x to the negative 1 dx. Like that's what we do if it's 1 over x squared, right? X to the negative 2. And then we use our power rule, which says add 1 to the exponent and then divide by that number, that new exponent plus 1. And that's where we come into a problem. So the reason we can't just use power rule if it's 1 over x is because you get this divided by 0 issue, and it's not always going to be true that this is just, oh, no solution, there's no area under that curve. There's almost always area under the curve, depending on what our bounds are. All right, so if we just practice this, the integral of 2 over x dx, remember you can pull a constant out in front. And so the integral of 1 over x dx is natural log of x. So this is going to be 2 natural log of the absolute value of x plus c. Now, since we're working with natural logs, if you are trying to look for your answer in a multiple choice question, remember we could use our log properties to work on this a little bit more. Like this is the same, this 2 out in front is the same as having natural log of x squared plus c, and that's a pretty common change to make because if this is x squared, then I don't really need the absolute value anymore because x squared is positive no matter what. All right, what about this next one? 1 over 4x minus 1. So this is a case where we'd have to do u sub because it's not simply 1 over x. So u is 4x minus 1. Du dx is going to be just 4. You can solve this for du if you want. Multiply dx over, divide by 4. Or you can, so that's going to put a 1/4 out here. Since dx is, since we're replacing dx with du times 1/4. Or you can think of it as like, okay, I needed a 4, I needed a times 4 here, so I'm going to balance it out with a 1/4 here. All right, so anyway, we should be able to get to a place where we have 1/4 the integral of 1 over u du. And so that's equal to 1/4 the natural log of the absolute value of 4x minus 1. I'm subbing my u back in, plus c. Number 3. I'm noticing that my denominator expression is 1 degree higher than my numerator. That's a pretty good indicator that u sub is going to work here as well. So u is x cubed plus x. Du dx will be 3x squared plus 1, which is what I have right here in the numerator. So this 3x squared plus 1 dx, that is du. So you can show yourself solve for dx if you want, show yourself canceling things, but this is just telling me, hey, you have 1 over u, and you already have du. You don't have to put any extra stuff in there to get du. So this is natural log of the absolute value of x cubed plus x plus c. All right. Number 4, u is going to be 3x plus 2. Du dx will just be 3. So you could solve for dx and then sub in, or you could say, okay, I need to get du, I need 3 dx. If I just do the multiply step, I need a 3 here, so I'm going to multiply out by 1/3 out here so that I can make that substitution. So we have 1/3 the integral of 1 over u du. So we have 1/3 the natural log of the absolute value of 3x plus 2 plus c. And again, remember, this could be, I didn't do this in a previous example, we had 1/4. Remember, this could be the absolute value of the cube root of 3x plus 2 inside of that natural log. Now, that would still need an absolute value because 3x plus 2 can come out positive or negative, and odd roots can come out positive or negative. So I would say when in doubt, keep your absolute value in there. And then you just have to know if they drop it in multiple choice, whether or not that was okay to do. For number 5, remember the derivative of tangent is secant squared. So if you make u equal to tangent of x, then du dx will be secant squared of x. So again, you have du right here. So no adjustments needed. We have 1 over u du. Natural log of the absolute value of tangent of x plus c. All right, what about my next one? So I could square this out, x squared plus 2x plus 1. But I don't know if that's going to be any faster or not. We could probably try it both ways. But what if we thought of like u just being, I want to show you kind of a trick. What if u is just x plus 1 because that's sort of the inner function? Then du dx would just be 1. So du is dx. And the only problem with this right now is like I have 1 over u squared du, but what's up with this 2x here? So you can show yourself solving here and saying, all right, u is equal to x plus 1. If I solve that expression for x, then u minus 1 is equal to x. And so if I want to get rid of this x up here, I can rewrite it as the integral of, and I can put the 2 out in front, make life a little easier. Instead of x up here, I have u minus 1. Or I could have made it 2u minus 2 if I wanted to divide by that, over u squared du. So you are allowed to manipulate this original u equation that you created to help you eliminate values of x that weren't canceling out. And then how does this help me? Well, remember, you can work on it further. So this 2 that's out in front would be the integral of u over u squared is just 1 over u du. And then this 2 comes along here too. So minus 2, because this is minus 1 over u squared. Minus 2 times the integral of 1 over u squared du. So you're allowed to divide and then split up those two terms. The 2 goes to both of them. 2 times 1 over u du is 2. Natural log of u is absolute value of x plus 1. Minus 2 not natural log. Going back here, remember, this is just u to the negative 2. So it's minus 2, and then when we add 1 to that exponent, we get u to the negative 1 over negative 1. Clean that up in a minute. So 2 natural log of x plus 1, or natural log of x plus 1 squared. Do that. And then negative 2 divided by negative 1 is going to be plus 2 over u, which is x plus 1, plus c. I don't want to take the time in the video to square this out, but what would have happened if you made it x squared plus 2x plus 1? Your du would have been 2x plus 2. And so you have a 2x here, but that plus 2 would have not really been able to cancel out. So or 2x plus 2 doesn't cancel with the 2x. So I think that we have the better way to go about this. Number 7, use implicit differentiation to find dy dx. So what is that again? That's where you have this equation in terms of both x and y, and we want to find dy dx. So remember, you differentiate with respect to x on both sides, and then any variable that's not an x gets that, in this case, gets a dy dx. Or if there were like t's in there, it'd get a dt dx, whatever. So you get a little extra chain rule for any non-x terms. So the derivative of 3x is just 3 minus 2 times the derivative of natural log y is 1 over y. But then again, this is a y, so you need to say times dy dx. That's chain rule. Plus derivative of y squared is 2y. Again, dy dx. And derivative of a constant is 0. Next step is to get your dy dx's on the same side and your non-dy dx's on the other side. So I can say, and then factor, remember, dy dx from this side, I'm going to say that's 2y minus 2 over y. And then it would equal, I would subtract 3 to this side. So dy dx, now we can clean this up quite a bit, but for now it's negative 3 divided by 2y minus 2 over y. Chances are, if you're searching for an answer in a multiple choice, it will be simplified. I would multiply by negative y over negative y because I don't like when I have single terms that are negative. But you could also just multiply by y over y. So an equivalent answer that gets rid of the complex fraction would be positive 3y. And then these two terms are going to flip around because the second term is going to become positive. Negative 2 over y times negative y is 2. And then minus 2y times negative y. So minus 2y squared. I could factor a 2 out. If it's free response, I can leave my answer like this. So it all just kind of depends. All right, for our next one, again, we're going to differentiate, take derivatives with respect to x on both sides. The derivative of natural log of xy, excuse me, you could do this two ways. You could split this up to begin with. This is natural log of x plus natural log of y minus x squared on this side, and then take the derivative. That's probably a lot easier. Or you could say, oh, it's 1 over xy times product rule with xy. I think I might have done that in the homework now that I think about this. But anyway, I would expand first and then take the derivative. So the derivative of natural log x is 1 over x, plus the derivative of natural log y is 1 over y, dy dx, minus 2x equals 2 dy dx. That's probably way easier and a lot less ugly compared to the one that I have in my homework, I'm sure. Okay, so I'm going to move dy dx's to the right side. 1 over x minus 2x is equal to 2 dy dx minus 1 over y dy dx. If you factor a dy dx out and then divide by that quantity, the complex fraction version is 1 over x minus 2x over 2 minus 1 over y. Again, if it's free response, you can leave it like that. If it's multiple choice, you might be searching for your answer. To get rid of the complex fraction, the common denominator across the entire complex fraction is xy. So if you multiply by xy on the top and the bottom, distribute things through correctly, you get y minus 2x squared y divided by 2xy minus x. And yeah, you can factor a little bit, factor out a y, factor out an x. You're looking for equivalent answers at that point. Find the area of the region bounded by the graph of y equals, of y equals x over x squared plus 1, the x-axis, and x equals 3. Might be a good idea to sketch this. Maybe. So the x-axis is here. x equals 3. Like if I plug 3 into this, I get 3 over 10. If I plug in 0, I get 0. And it's probably got some sort of a curve like this. So the x-axis. Yeah, and so the x-axis, the only 0 is 0. So even though this does probably come up on the other side, we're only looking at this region here. All right, so find the area of that region. That would be the integral from 0 to 3 of x over x squared plus 1 dx. And then we have u sub, so u would be equal to x squared plus 1. Du dx would be 2x. So du is 2x dx, right, before you solve for dx. You have x dx. If you need a 2 here, you balance it out by multiplying a 1/2 out front. So you've multiplied by 1. It's just a fancy version of 1. All right, so we have 1/2 the integral. Now, do I want to change my bounds here? Maybe. That part's totally up to you. No one's going to be looking to be like, oh, they wrote 0 and 3 here. That's not in terms of u, even though they have 1 over u du. It's just up to you how you want to do it. So if I change those bounds, if I put in 0 for x, then the lower limit for u is 0 plus 1 is 1. If I put in 3 for x, then I get 10 up here. I tend to go back and forth with how I do this, so I don't know. If you're going to change your bounds here, though, keep things in terms of u. That's the only thing that you have to be careful of. You don't want to switch it back to x squared plus 1 and then plug in 10 for x when really that's u. So 1/2 natural log of 10 minus 1/2 natural log of 1. They will always want you to simplify natural log of 1. That's just 0, right? E to the what equals 1. That's just 0. So really this is 1/2 natural log of 10, or natural log of square root of 10. Either way, be able to find both answers depending on what the problem is. Or natural log of 10 divided by 2. Solve the differential equation dy dx equals 1 over x natural log x. So if I'm solving a differential equation, I'm trying to integrate both sides with respect to x so that I can get y equals. So y equals. Now down here, if I let u equal natural log of x, that's good because du dx is 1 over x. And so you have 1 over x dx. So you don't have to do any extra work here to set up your 1 over u du. No extra coefficients needed. So y is equal to the natural log of x plus c. And do I need a little absolute value here? Well, they didn't have one in this problem, so it is just understood there is a domain restriction here where x can only be greater than 0 on this function. If I were to graph 1 over x natural log x, it should only exist for values greater than 0. All right, we need a calculator for this problem. A population of bacteria is changing at a rate of dp dt equals 3,000 over 1 plus 0.25 t, where t is in days. The initial population is 1,000. Write an equation that gives the population at any time t, and then find the population when t is in 3 days. This might be in our homework too. I don't know if it's the exact same thing or a slight variation. All right, so first, write an equation that gives the population. So if you have dp dt, find p by taking the integral with respect to t of both sides. The integral of dp dt is p. I'm going to write p of t, population function in terms of time. What is that equal to? Well, the 3,000 can come out. 3,000 times the integral. It's an indefinite integral. We'll have to use our initial condition of 1 over 1 plus 0.25t dt. So over here, I've got to do a little u sub. Oh, wait, do I have to? No, yeah, sorry. I almost hopped to my calculator, but I forgot. This is not a definite integral, so yes, even though we're allowed to use a calculator, we can't use it yet. So this would be 1/4, right? And so I don't have a 1/4, I just have a dt. So if I need a 1/4 in here, then I need to multiply by 4 on the outside. So we're not quite used to that. If you don't like that, solve for dt. And in for dt, you'd be subbing in a 4 du. I'm putting the 4 out in front because it's a constant. So instead of 3,000 out here, we actually have 12,000 times the integral of 1 over u du. So p of t is equal to 12,000 times the natural log of 1 plus 0.25 t plus c. We need the equation that gives the population. So now we use that initial condition. P of 0 is 1,000. So the population is 1,000 when t is 0. 12,000 times the natural log of, when t is 0, this is natural log of 1. And remember, natural log of 1 is 0. So c equals 1,000. So P of t is equal to 12,000 times the natural log of the absolute value of 1 plus 0.25 t plus 1,000. So here's our equation that gives the population at any time t, and then find P of 3. This is where you finally get to use your calculator. $12,000 times the natural log of 1. If I put in 3 for 3, right? Yeah, if I put in 3 for t, I'm going to get 1.75. 1 3/4, and then plus 1,000. So I'm going to keep this to 3 places. So 7,715.389 bacteria. And maybe I'll round that to 7,715 bacteria. All right, so every trig function does have an antiderivative. Up to this point, we only knew these first two. We knew the integral of sine of u du is negative cosine of u plus c, and we knew integral of cosine of u du is sine u plus c. But now we have these other ones for tangent, cosecant, secant, and cotangent. And like thinking off the top of my head, the tangent and cotangent ones could be easily reworked with u sub, because tangent is sine over cosine, cotangent is cosine over sine. So since those are derivatives of each other, you have your 1 over u du situation. These two are harder to work out. And when I was doing the homework, I started doing one of these, forgetting that I had these rules written out, and I got a different answer, and I messed up somewhere along the way. So these are harder to memorize. To be honest, I don't have them memorized because they don't pop up all over the AP test. They're kind of obscure. But any of these, 1, 2, 3, 4, could pop up on the AP test because you should have sine and cosine memorized, and you can easily figure out tangent and cotangent, since tangent sine of u over cosine u, and cotangent is cosine u over sine u. So anyway, we will have to be referring back to these, probably doing homework and stuff. All right, so number 1, we have, number 11, we have the integral of 2x over x plus 5 squared. So again, you can think about saying like, well, what if this is x squared plus 10x plus 25? But then you're going to get du is 2x plus 10, and you only have 2x here. So anyway, so when I see this, instead of FOILing something out, I'm going to use the trick we used earlier and say u is x plus 5. Du dx is 1, so du is dx. And so how do I take care of this problem of a 2x? I solve this equation, u equals x plus 5, solve it for x. U minus 5 equals x. And then sub that in for the x that you want to get rid of. So I'm going to pull the 2 out in front. The x in the numerator is now u minus 5, and the x plus 5 squared is now u squared, and the dx, remember, is equal to du. And that can be split up. That is 2 times the integral of, if you divide, which you always should, u over u squared is 1 over u du, and then minus, this 5 is going to come out, so minus 10 integral of 1 over u squared, or u to the negative 2 du. I kind of like to write my 1 over u squared like this so I don't accidentally write it as natural log of something. So this is 2 natural log of the absolute value of x plus 5, oops, minus 10, and then this is going to be times u to the negative 1 divided by negative 1. So 2 natural log of x plus 5 plus 10 over x plus 5 plus c. All right, what about cotangent? So cotangent of pi theta. Let's let u equal pi theta. Du d theta would just be equal to pi. We don't have a pi out here. We need a pi d theta, so we multiply by 1 over pi. So we have 1 over pi times the integral of cotangent of u du. And we refer back to our little cheat sheet up here. That's going to be 1 over pi times the natural log of the absolute value of sine of u, which was pi theta, plus c. So you do not have to show that this is cosine over sine. If you have this memorized, you can jump right to it. But if you don't, it's a quick rewriting as cosine over sine, letting u equal sine of pi theta, and then figuring out du from there. All right, number 13. So let's let u equal x squared plus 4, because I certainly don't want to cube anything out. Du dx is 2x. I have an x dx, I just don't have the 2. So if I want the 2, I put it there, and then I balance by putting a 1/2 out in front. So I have 1/2 the integral of, it's 1 over u to the third, or u to the negative third du. So no natural logs needed here. 1/2 times u to the negative 2 divided by negative 2 plus c. So that's negative 1 over 4, and then times the quantity x squared plus 4 squared. All that's in the denominator. And the 1 is negative, plus c. All right. Oh, now prove this one. Okay, fine. I kept saying, oh, you can quickly do it. So let's show that the integral of cotangent x dx is the same as the integral of cosine x over sine x dx. And then we would say u is going to be sine x. Du dx is going to be cosine x. We have cosine x dx, so we have du. So this is equal to the integral of 1 over u du, and that's equal to the natural log of the absolute value of u, which was sine x, plus c. Number 15, wait a minute. Didn't we just do this? Number 15 is the same as 5. We're not doing it again. C5. Okay. Number 16. If you have a monomial, remember, you should always just divide both terms or all terms by that monomial. We have the integral of 1 minus 3 over x cubed dx. We don't need u sub for any of this. The integral of 1 is x. Remember, this is negative 3x to the negative third. When you add 1 to that exponent, you're going to get x to the negative, so minus 3x to the negative 2 over negative 2. So you have x plus 3 over 2x squared plus c. All right, now 17, this one's weird because u sub is like if u is equal to x minus 1, then du is dx. And like, what about this x plus 5? You can do this a couple of ways. You can do our trick, solve for x. So u plus 1 is equal to x. And then you can say, all right, this is the integral of u plus 1 plus 5, u plus 6 over u. And that is equal to the integral of 1 plus 6 over u du. And that is equal to u plus 6 natural log of the absolute value of x minus 1 plus c. Another way to do it is to do a quick round of long division. X plus 5 divided by x minus 1. X goes into x once. You have this remainder of 6 over x minus 1. So you have the integral of 1 plus 6 over x minus 1, and that's the same thing that we had here. I prefer the first method, but both of them work. All right, and then finally, tangent of 1/2 t. So u is 1/2 t. Du dt is 1/2. We need 1/2 dt, so we balance it out by putting a 2 out here. 2 integral of tangent of u du. Now, what's tangent's little thing? It is negative natural log of absolute value of cosine u plus c. So this is equal to negative 2 natural log of the absolute value of cosine of u, which was 1/2 t, plus c. All right, so keep these notes out as you're doing the homework. When you're checking my key, I may have done some of these the long way, forgetting that I had these shortcuts. But either way works.